Hello viewers, good morning. Myself Dr. T. N. Oza here, retired professor of chemistry. After a long gap, I'm again going to present a video on a very important topic of spectrometry known as mass spectrometry. Mass spectrometry is an analytical technique of extreme importance. The technique finds much use in every branch of chemistry, including pharmacy, medical sciences, biology, etc. These are the points which we will discuss one by one later. These various points will be covered in this video. Mass spectrometry is essentially an extremely important chemical analytical technique for molecular structure determination. This technique also provides other useful data like accurate molecular weight, molecular formula, elemental composition, ionization energy of molecules, novel reaction intermediates, etc. In this method, a molecule, say M, is first ionized to give molecular cation radical, which then suffers extensive bond cleavage, produce smaller ions known as the daughter cation. The mass spectral data is presented as a bar graph showing mass to charge, that is m by z, along the horizontal axis versus abundance of ions along vertical axis. The identification of these ions leads to the structure of the molecule. The instrument used for this technique is called mass spectrometer. A mass spectrometer is a highly sophisticated instrumentation, very costly indeed. Basically, it consists of the following components: an ion source in which the neutral molecule M is ionized to give cation radical by using a number of techniques. This molecular cation radical possesses very high vibrational energy. Consequently, it undergoes bond cleavage to produce smaller cations M plus and M plus dot. The second part of this instrument is known as electrical field E. This field accelerates the ions toward the recorder device. The moving ions are deflected by a magnetic field B so that they reach the detector separately. Next part consists of amplifier, detector, dedicated computer, and accessories. Block diagram is shown below. It is ion source, ion accelerator, ion deflector, ion charge amplifier, detector, etc. Ionization of sample molecule M to give highly energetic molecular cation radical are also called parent ion. This is the first step. In the second step is fragmentation, that is extensive bond cleavage of the molecular ion to yield all possible ions. These smaller cations are called daughter cations. Sometimes rearrangement ions are also formed. A typical example is shown here. Molecular cation giving daughter cation on M2, neutral molecules, atoms, etc. Then the subsequent step involves separation of all cations using electrical acceleration field E and magnetic deflection field B as a function of their mass to charge ratio. The mass to charge ratio is quoted as m by q, and some authors prefer m by z. Formerly, the symbol was m by e. Now it has been abandoned. Mostly m by z is used. Some authors prefer m by q, q for charge. Mostly the charge value z is 1, sometimes 2 for polycyclic aromatics. Negative ion mass spectrometry is also done, but it is very less common, sometimes used for nitro compounds and methoxy compounds. Subsequent step is amplification of the electrical charge of ions and their detection. Then the data are received by a computer. Data are presented as a bar graph showing mass along the horizontal axis and percent abundance of each type of cation vertical axis. This kind of graphical display is called mass spectrum. Mass spectrum. Now the question arises: what type of samples can be analyzed by the mass spectrometry technique? In principle, all type of samples, that is, gaseous, liquid, and solid, can be used. But those organic or inorganic compounds which are readily converted to vapor phase are very suitable for mass spectral analysis. How much sample is required? Very small quantity, 2 to 5 milligram, of course, highly purified sample is required. The sample is first vaporized, then it is bombarded with a beam of electrons carrying energy between 70 to 100 electron volt. This method is called electron impact method. Upon impact of these highly energetic electrons with the sample molecule, an electron is knocked off from the molecule, thereby causing ionization of the molecule to produce molecular cation radical, also called parent ion. Symbol is M plus dot or P plus dot. The molecular weight of these ions is same the molecular weight of the parent molecule. Now we must know what causes extensive fragmentation of the molecular ion. Why it undergoes fragmentation? So the reason is very simple. The ionization of most organic compounds requires between 8 to 20 electron volt energy. We bombard the molecule with a very high energy, 70 to 100 electron volt. Obviously, huge amount of energy surges through the molecular ion is produced in a vibrationally excited state. Therefore, it suffers extensive bond cleavage and bond rearrangements. This process, called fragmentation of the molecule, produces several smaller cations, generally named as daughter cations, symbol small m plus and small m plus dot. Also free radicals, neutral molecules, and atoms. But we measure only the positively charged ions. Few examples of fragmentation are as follows. Here we have taken a tertiary alkane. It is bombarded with electron E. Then one electron is knocked off from the molecule to produce molecular cation radical. It undergoes fragmentation to produce tertiary butyl cation in this case, whose M by Z is 57. Note that it is odd mass number, whereas the molecular cation radical is at even mass number. In this case, the most abundant ion, that is percent A equal to 100, is called base peak and is a simple tertiary butyl cation, not a cation radical. Note that a rule called the nitrogen rule of organic chemistry is stated as follows. All organic compounds containing 0 or an even number of nitrogen atoms have even molecular mass, and they show the molecular cation radical at an even mass number, whereas the normal daughter cations are simple cations occurring at odd mass number. This is very important rule. I repeat the rule. If a compound does not contain nitrogen or it contains an even number of nitrogen atoms, then what will be the case? The molecular mass number of the molecule will be even number, and also the molecular cation radical will be at even mass number. But the fragment ions will be at odd mass number if they don't possess the radical character. However, if the daughter cations also possess radical character along with the positive charge, again their mass number will be even. When the molecule contains one nitrogen or three nitrogen atoms, that is odd number of nitrogen atoms, the reverse statement applies. That is, the molecular mass number of the original molecule will be odd, not even. And in this case, the parent ion will have odd mass number. The daughter cations will have even mass number. But if the daughter cation is formed via rearrangement, then its mass number will be odd like the parent ion. This is a very important rule. You should remember where we will put a dot, we will not put a dot. This has to be understood clearly. Next, we discuss one more example. This is a benzyl derivative undergoes ionization to produce molecular cation radical, which undergoes fission, that is cleavage, to produce benzyl cation. This benzyl cation immediately rearranges to a seven-membered ring propylium cation, which is more stable due to resonance. Its mass number is 91. Here I would like to tell you a very, very important point. If the mass spectrum of a compound contains a very intense peak at m by z 91, you can be almost sure that part of the structure of the molecule is a gene ring attached to CH2. Other parts you should be learning about. But a base peak at 91, that is very strong peak at 91 mass number, indicates the presence of 66H5CH2 part in the molecule. One more example is given here, a molecule which is a carbonyl compound. Upon ionization, one electron is removed from where? From oxygen atom. And a molecular cation radical is formed. Now, under certain conditions, it can undergo rearrangement reaction known as McLafferty rearrangement to produce daughter cation, which is both cation as well as radical. The mass number will be even. This McLafferty rearrangement, which is very important rearrangement of mass spectrometry, it is actually a thermal elimination reaction. It is possible only in those cases where a carbonyl group is situated gamma to a CH2 carrying hydrogen. If this kind of arrangement is not there, then McLafferty rearrangement won't take place. So, presence of McLafferty rearrangement ion in the mass spectrum of a compound helps us reveal the structure of the molecule. This concept is very, very useful in distinguishing various carbonyl compounds, aldehydes, ketones, amides, pattern of substitution. You should solve few more examples to understand this properly. Now, one more rearrangement is very common in mass spectrometry. This is known as ortho effect. For example, suppose we have orthonitrotoluene, metanitrotoluene, paranitrotoluene, then the ortho isomer will show this effect. Again, a thermal elimination reaction. Removal of water molecule from the molecular cation gives a peak at even mass number. Thus, we can distinguish between ortho substituted nitrobenzene and meta and para substituted ones. Many other examples of this kind are mentioned here. For example, benzene ring carrying two substituents, OH and CH2OH. If they are at the ortho position, then McLafferty rearrangement, thus ortho elimination will take place, otherwise not. Now, what is the mass spectrum? The spectrum is shown here. I have taken this diagram from my own book on spectroscopy, chapter number 10. See, bar graph is called mass spectrum. What are the variables? Along the horizontal axis, you have mass. Actually, m by z is essentially mass because z is usually 1. Along the vertical axis, you have percent abundance of each kind of ion. The most intense ion, most abundant ion, giving 100% abundant peak is called base peak. In some cases, the molecular ion peak may be base peak, not in all cases. Mostly the base peak is a small peak, small molecule, small cation. Then the molecular ion peak is visible, not in all cases, in some cases. Then there are isotopic peaks. Why isotopic? We will discuss it later in detail. In nature, there are two types of carbon, carbon 12, carbon 13. Carbon 14 is negligible. Similarly, in nature, there are two types of chlorine atoms, chlorine 35, chlorine 37. Three type of sulfur atoms, sulfur 32, 33, 34. Two kind of bromine atoms, 79 and 81. Two kind of boron atoms. So due to the presence of these isotopes, sometimes we also see isotopic molecular ion peaks, M plus 1, M plus 2, M plus 3. So I repeat, a mass spectrum is a bar graph. It shows vertical lines which are called mass spectral peaks. The peaks are variously named: base peak, fragment ion peak, molecular ion peak, isotopic peaks. One more term is there, metastable ion peak, which we will discuss later. What are some common ionization methods in mass spectrum? As I told you, electron impact method does not work for every kind of. Most of the molecules can be handled by this method, but there are some other methods also. When EI method fails, other methods are adopted. One method known as chemical ionization is very popular. It is very simple also. What happens in this method? If the molecular cation radical cannot be detected by the EI method, then chemical ionization method can be helpful. In this method, what happens? The sample is mixed with methane gas. In the next slide, we will discuss that. Here in this slide, we will name most of the methods which are used in mass spectrometry. These methods include fast atom bombardment, field desorption, laser desorption, plasma desorption, secondary ion mass spectrometry, thermal ion mass spectrometry, etc. Some other methods are also there. So you should remember, in mass spectrometry, a number of ionization methods are used. Which method is applicable to which kind of compound is our choice. Now, what happens in the CI method, chemical ionization method, where the sample is very much unstable for the EI method, its molecular ion can often be detected by the CI method. In the CI method, sample is first diluted with methane. Upon electron impact, methane molecules produce methane cation radical, which undergo fragmentation, produce H atoms and H plus ions in large excess. The reaction between the sample molecule M and hydrogen ion produces detectable MH plus. Note that here this ion has molecular mass 1 unit larger than the mass of M. But this method is used for determining the molecular weight of some compounds. In FI method, that is field ionization method, ionization of the molecule is caused by high voltage positive field which pulls out an electron from M, thereby converting it to M plus. I have shown this in diagram later. In the fast atom bombardment, that is FAB method, it is applicable to non-volatile compounds. The sample is placed in glycerol or some other condensed matrix and it is bombarded by energetic xenon atoms or helium atoms. The macromolecules do not give detectable molecular ions by common ionization methods. The method used for them is matrix assisted laser desorption ionization, time of flight. Short form is MALDI TOF. Another method is electro spray ionization method, particularly useful for the mass spectra of macromolecules. Electrospray method is used for negative ion mass spectrometry, not very common. The mass spectrometer and a typical mass spectrum. Again, I have taken this diagram from my own book. You see a tentative diagram is shown here. There is a sample inlet chamber having very, very low pressure, 10 to the power minus 5 torr. The sample is injected into this chamber. Then the next chamber is ionization chamber. Its pressure is 10 times lower than the pressure in the sample inlet chamber. So vapor phase molecules are automatically drawn into it. Then a filament produces electrons. Energy of these electrons is increased by accelerator. Negatively charged plate, it repels the electrons by 70 volt current. So the kinetic energy is raised. These electrons hit the molecules to cause their ionization. And the molecule, after ionization, decomposed into cations, free radicals, atoms, neutral molecules. The vacuum pump draws out all but cations. Cations are not drawn. Next, they pass through the circular tube, semicircular tube. An electrical field accelerates them and a magnetic field deflects them so that they reach the ion collector and detector system at different points. Otherwise, it will be impossible to detect the ions of different types. But here the magnetic field deviates each kind of ion from their path. The ions having lower mass are deflected more. This question is sometimes asked. Remember, the ions of lower mass are deflected more than the ions of higher mass. The purpose is to separate the ions so that they can reach the detector at different points. Now the data is output as a bar graph, as I shown earlier, abundance versus mass. The lower diagram is showing how those molecules can be ionized which are unstable. A very, very high positive voltage is applied. So an electron from the neutral molecule is pulled out and the molecule becomes ionized without being hit. Here, the heading says appearance, potential, and molecular ionization energy. A very, very important concept. When the electron energy is increased at a certain point, ionization of molecule will take place. So if we can accurately, precisely measure how much voltage is required to cause ionization, we can determine the molecular ionization energy, a very, very important molecular property. Then metastable ion. I had told earlier about this. Sometimes the mass spectrum produces metastable ion. See, the normal mass spectral peaks of daughter cations typically appear as sharp lines at integral mass number in low resolution. Occasionally, few broad or diffused peaks of very low intensity appear at fractional mass value. These peaks are called the metastable ion peaks. The metastable ion peak arises as follows. Suppose ions of mass M1 leave the ionization chamber and reach the detection device and are recorded as usual, while few of these ions get decomposed en route field free zone, that is between the ionization chamber and the ion accelerator zone, giving a smaller ion of mass M2. The latter ion having a different mass than M1 will be displaced from the original path of ion M1 and will be recorded at a mass M star given by the formula M2 square divided by M1. Using this relation, we can calculate ion M2 and explain the decomposition pathway M1 giving M2 neutral fragment M3. An example is the decomposition of the ion cyclic C5H5 positive ion, mass number 65, giving cyclic C3H3 ion, mass number 39, and a neutral fragment acetylene. Examples of mass spectral analysis. Here I have taken one very simple example, very interesting one. The mass spectrum of an organic compound shows two molecular ion peaks at M by Z values 66 and 64. The corresponding heights of lines or the peaks are in the approximate ratio of 16 is to 50. We have to deduce the structure of the compound. No other information is available. I repeat the question. The mass spectrum of a compound shows two parent ion peaks at values M by Z 66 and 64. The intensities of these peaks are in the ratio 16 is to 50. Then how can we determine the structure? This much is given that the compound is an organic solution. We tabulate the data like this. The normal molecular ion M plus dot and the isotopic, because the difference between 66 and 64 is 2. So we presume that the other peak is isotopic peak, M plus 2. By Z values we have noted here. 64 for the normal isotope, 66 for the heavier isotope. Percent abundance 50 is to 16. Let us convert it to 100, multiply by 2, so it becomes 100 ratio 32. You can see this is nearer to 3 is to 1. Now our common knowledge shows that chlorine is such an element which has two isotopes in nature, chlorine 35 and chlorine 37. They occur in the ratio 1 is to 3. From this much information, we can conclude that the given sample contains one chlorine atom. Now the mass of chlorine is 35 or 37. If you subtract this mass from 66 and 64, we are left with 29. From this, we can very clearly, very confidently see that the compound is chloroethane. In one case, the isotope is chlorine 35, having molecular mass 64. In other case, the isotope is chlorine 37, having molecular mass 66. So in this manner, we can determine the structure of simple molecules from isotopic peak heights. Mass spectra of metal carbonyls. For metal carbonyl compounds, mass spectrometry is very, very useful in determining how many CO groups are there in the molecule and how is their bonding, whether in a bridged position or terminal position. The electron-spray mass spectrometry is a kind of negative ion mass spectrometry using methoxide ion spray technique. It is a powerful tool for revealing the structure and bonding of metal carbonyls. But for the volatile metal carbonyls, the normal EI method is also useful. Successive splitting out of neutral CO moiety, mass number 28, from the molecular cation produces fragment ions, and we can determine how many CO ligands are there in the complex compound. Then, how do we calculate the number of carbon atoms in a compound using mass spectrometry? You see, the natural abundance of carbon 13 isotope is nearly 1.1% as compared to 100% for carbon 12 isotope. Evidently, the intensities of the molecular ion peak M plus dot and the carbon 13 isotopic peak M plus 1 peak will be in the ratio 100 ratio 1.1 times number of carbon atoms in the molecule. Therefore, number of carbon atoms Nc equal to 100 times M plus 1 intensity divided by 1.1 into M intensity. For example, for a certain hydrocarbon, assuming formula CnHY, the percent abundances of NM plus 1 peaks were found to be 54 and 66.3. 54 and 6.3. We have to calculate how many carbons are there in the molecule. Therefore, we calculate Nc equal to 100 multiplied by 6.3 divided by 1.1 multiplied by 54. We get the number 10.6 rounded to, there is some mistake. It is uh, 10.6 rounded to 11. It should be 11. Now, another example, where the compound also contains heteroatoms such as nitrogen or oxygen. For each additional element present, increments per heteroatom are as follows. M plus 1 due to nitrogen 15, 0.37, due to oxygen 17, 0.04, due to sulfur 33, 0.80. M plus 1 contribution will be like this. M plus 2 contribution, N15 0, O18 0.20, sulfur 34 4.44, chlorine 37 32.5, bromine 81. This rule can be applied follows for the given formula. C3H7NO2 assuming M peak equal to 100%. So the calculation is shown here. Now I have given a table which speaks of some typical compounds. From the mass number, we can assume the structure of the compounds. This table is very helpful. Here I have taken one example showing fragmentation pattern. Is 2-methyl pentane. You see how the molecular ion undergoes fragmentation. The molecular ion having mass 86 undergoes fragmentation. Methyl group is knocked off, giving C5H11H plus. Another fragmentation creates ion of mass number 43, the base peak. So this type of problem, simple problems like this can help us understand the technique and its application. Thank you.